So, volume-wise, can you all hear me?
Yes.
Okay, if I start speaking too low, just signal to me to shout. But yeah, let's get started. So, like many developers, I love working on code performance. Just getting deep into a problem, measuring, profiling, tweaking, squeezing out every last drop of juice from my code. I'm a back-end Rails developer, so I don't get to do that very often. But last year, I worked on this project where performance was key, and working on that project, I learned some interesting lessons. This is a talk about assumptions. First of all, though, hi, my name is Daniel, and I work for a company called GoCardless. We are a payments company based in London. As you probably noticed, I'm not originally from London. I come from Argentina, so in case you were wondering, that's the accent. And before I get into the actual interesting part of the talk, I need to give you a little bit of a background of the problem that we were trying to solve. GoCardless is a bank-to-bank payments company. We're sort of an API on top of the banking system. When you're a payments company, customers expect you to always be available, just like they expect your electricity to always work. And that means for us, uptime is critical, and it means, among other things, having good metrics for our apps is critical. And this is where our project came in. One of the main tools we use for this is a metric server called Prometheus. Now, we love Prometheus, but we had a pretty big obstacle trying to get it to work with Ruby. Now, Prometheus basically keeps a history of what all of your numbers look like over time. And to get those numbers, it will periodically hit your app asking for them. So in order to have metrics, you're going to have your web server that's running your app. And in addition to that, it's going to keep a bunch of counters in it, say how many HTTP requests you serve, how many payments you took in different currencies, etc. Prometheus hits your app every few seconds, asking for those numbers, and your app responds with something that looks a bit like this. Now, Prometheus also has libraries that help you do this. These libraries run inside your app, and you use them to declare your metrics, you set their values, and then when Prometheus scrapes you, they automatically generate this output. And there's one for all major server languages. There's one for Go, there's one for Java, and of course, there's one for Ruby. And for most languages, the story ends there. You just declare your metrics, you set their values, and then everything is fine. But in Ruby land, and by the way, also in Python land, the story is a little bit trickier, because Ruby and Python have a global interpreter lock, or GIL, which basically doesn't let you run your Ruby code in multiple threads at the same time. Because of this, our servers tend to not be multi-threaded. We use separate processes instead, because threads don't parallelize well. When you have separate processes, these processes don't share memory, which ends up solving the same problem the GIL was solving, and everybody can happily run in parallel, ignoring each other. In the web world, we call this a pre-fork server, and it's how Unicorn works. When Unicorn starts, it will load your app, and then it forks itself into a master orchestrator process that is listening to requests, and a bunch of worker processes that are actually working on them. When a request comes in, the master sends the request to a worker that is free, then takes back the response and sends it back to the client. Now, the system works great, it scales really well across cores, and it's how the majority of Ruby web apps are running in production. But for the Prometheus use case, this is a bit of a problem, because now that we have separate processes and they don't share memory, each process will have its own internal counters. When Prometheus hits you and asks for your numbers, the master process will pick a worker, and that worker will report its numbers. But this is never what you want, because this is a partial view of the system. What you want is a view of all of these counters added together, right? But because the processes don't share memory, there's no way for any worker to see the numbers in the other workers to be able to add them. This is by design, and it's the main reason we use multiple processes, but for the Prometheus use case, this is a problem. And so, since most Ruby web applications are running in multi-process servers, and since the Prometheus Ruby library didn't support an aggregation across processes, it basically means that most Ruby projects that want to use Prometheus basically can't. And we definitely had this problem. We were using Prometheus, we wanted to have metrics for our main Ruby app, and we couldn't. And it wasn't just us. This has been the case for quite a lot of people for quite a lot of time. And also, the Ruby library was one of the first libraries to be made, and it was done very early in the lifetime of the Prometheus project. And that means it was made before we had figured out a bunch of what the best practices are supposed to be, so it didn't really adhere to these best practices. And so it had a bunch of other issues that were a problem for us. Now, there were some workarounds. Most notably, GitLab forked the main Ruby library for Prometheus, and they had a multi-process solution, but it wasn't getting merged into the official repo, and it also shared all of those other problems with best practices. So we didn't want to use this one, and we didn't want to have yet another fork. So instead, we got in touch with the maintainers. We all decided on roughly a plan of action, And we decided we would do a rewrite that would pretty much fix all of the things. But there's one more thing to consider. The Prometheus maintainers really care about performance for these libraries, because instrumentation should be free for your app. If you want to increment one of these counters in a tight loop inside your app, you should be able to do that and not even notice. And buried in the long thread in the GitHub ticket, we had an actual target, right? I've changed the names to protect the innocent, but basically one of the maintainers said that incrementing a counter shouldn't take more than a microsecond. Why a microsecond? I don't know, but that was his target. And if I wanted to get this thing merged, we're going to have to get there. Now, another maintainer of the gem who had more experience with Ruby, very reasonably going like, yeah, you're not going to be able to do that. To which the first guy, very reasonably was like, I mean, surely Ruby can't be that slow, right? Which leads to one of my favorite answers ever in open source. I guess there's a reason people like writing C extensions. But anyway, whatever we did to solve this, it had to be fast, and we had an actual target. And there was one more thing that we wanted to do, and the maintainers of this library agreed, which is we wanted to have separate stores for these numbers. So in this library, we have these metrics classes that you use to declare your counters and set their values, and they stored the numbers in an instance variable. We wanted to change this so that the numbers would be stored somewhere separate. We wanted to have these stores that were basically interchangeable, and we wanted to keep all of the numbers there. So we would go from something like this to something a bit more like that. And the reason for this is that different projects would have different needs. Some people will be running on a single thread, a single process, and really care about performance, whereas some other people will have a web app and have multiple processes and be hitting a database over the network, so who cares about microseconds at that point anyway, right? So we wanted to separate this, and one of the side effects was having these interchangeable stores gave our users much better choices, right? They gave them more choices, but it also made our lives much easier, because if you remember, the difficult bit about this project was trying to share these numbers in a way that, between the processes in a way that was fast, right? Making these interchangeable stores meant that we could very quickly experiment with new ideas. All you had to do was do a little store, put it there and measure it. We didn't have to touch anywhere else in the code because it was separated. So it was a really good pattern for experimentation. So to recap, we were going to rewrite this gem so that it would support prefix servers. We're going to abstract away the storage of numbers. It was going to follow all of the current best practices from Prometheus, and it had to be fast. And basically, this is where we were at. We now need to figure out how we were going to do this in a way that actually solved the problem and stayed under that performance budget. Now, to store numbers, we use hashes instead of plain integers for reasons that are going to make a bit more sense later. But what this means for now is that when I say increment a counter, what I mean is you read and you write a value in a hash. And according to this exchange, this either could or couldn't be done in a microsecond. Now, I don't know about you, but if you had asked me back then whether you could do this in a microsecond, my answer would have pretty much been like, yeah, because I have no intuition of Ruby performance at this level. One guy here implied Ruby is very slow. The other one says doing this to a hash should be very fast. But this is such a tiny scale compared to my usual experience that I have no idea which one is right. What I mean by this is my entire Ruby experience has been pretty much as a backend Rails developer, right? So I'm used to a wall of performance that looks a little bit like this. Imagine this is a second. That is 1,000 squares, 1 millisecond each. As a web programmer, this is how I see the world. Time exists in boxes of milliseconds. There's nothing smaller than that for me. So I'm running my web app, and a request comes in. There's a couple of milliseconds that are taken by Unicorn, Rack, Rails, Meterwells, I don't know, but before it even hits my code, I just lost 2 milliseconds. Now there's a user ID in session, so we're going to hit the database to load that user. And it's a very well indexed table, so it comes back really quickly, say in 1 millisecond. Now the page we're loading is a list of orders for this customer, so we're going to hit the database to load those orders. And we're going to hit it again to load the lines for those orders. Then we hit it a bunch more times because we had an n+1 that we didn't know about. Oops. We check a couple of feature flags in Redis, which is super fast, but it's still at the other end of a network cable, so it's about another millisecond. And then we take all of this information and we render a view, which is actually quite big, so it takes a while. So that's what, 60, 70 milliseconds? That's reasonable for a Rails app. Like this may be on a good day. On a bad day, it may look a bit more like that. But I mean, who's counting? But the point is, this is basically my daily life as a Ruby dev. This is where my intuition works. This is where, if we need to care about performance, I know roughly how long things take, and so I can see if something is off and take a look there. But for other developers, this is very different. For example, if you're a game developer, you live and die in 16 millisecond buckets. If your game is going to run at 60 frames per second, you get 16 milliseconds per frame, non-negotiable. And in those 16 milliseconds, you need to process your inputs, run your AI, all of your game logic, your physics, your collision detection, make some pretty particle system, take all of that and render a pretty frame. And if you miss the 16 millisecond boat, you skip a frame, your game stutters a little bit, and then thousands of angry gamers will shout at you on Twitter. It's a little terrifying for me. And here, if you're a high frequency trader, you're just dying of laughter at this point. Like 16 milliseconds is an unthinkable luxury, right? If you take one entire millisecond, you're dead in the water. You can't even play this game. So the point I'm trying to make here is that what's fast and what's slow is really, really very relative. I mean, you have some people over here that are trying to get the memory to be in big chunks all together, so the CPU caches are full and they shave some nanoseconds. Where I'm over here in milliseconds land, try to maybe not hit the database too much. Like the difference in scale is insane. And so this is something really important to keep in mind when you're talking about performance. Some things that to me, as a Ruby developer, are super fast, somebody that's writing drivers inside the kernel, they can't even consider them because of how slow they are. So keep that in mind when somebody says that something is fast or something is slow. That is literally meaningless without a context. But we don't think about it like that most of the time. We just go with this is fast and that's slow, and we internalize that as if it meant something. Well, going back to the original question, can we do the thing with the hash in a microsecond? Well, as I said, I'm used to these sorts of timings. Like for the most part in my work life, time exists in milliseconds. Like I cannot care about anything smaller than this. I have bigger fish to fry. So when you ask me, can we increment a hash in a microsecond? A microsecond, that's this much. In case you can see that, it's a tiny dot over there. So if you ask me, can you do this tiny, tiny thing in a microsecond? I have no idea. I live in milliseconds land. But we have two opposite opinions here. Surely we can at least figure out who was right, right? Here's the fun thing. They both kind of work. Now let's go measure and see what we find. The first problem you have is even measuring this is not trivial. The way you would normally test this kind of micro performance is use benchmark IPS. Basically, you give it a bunch of ways of doing something, it will run them repeatedly, and it will tell you how many times per second you got to do them. The problem is, when the thing you're measuring is this tiny, the measuring itself is a significant part of your runtime. Now, the method is still useful when you're comparing different methods because it will tell you which one is faster. The overhead is reasonably constant. But it's not going to help you answer how long does it take to do X when X is tiny. For example, if I run this on my laptop, it tells me you can do that about 5 times in a microsecond, which is great, but it's a lie. Because here's the thing, for each iteration, I need to call a block. And calling a block is really fast in Ruby, but compared to other fast things like setting a hash, it's now a good chunk of your runtime. If, for example, you do this and stop using the block, it's now twice as fast, which is a bit closer to the truth. And if you want to get even closer, we can just time the empty loop, see how long the overhead is, and subtract them, and you get something like this. You can set a hash key about 12 times in a microsecond, which is awesome. This is well under our budget. And that's it, right? Like we have our answer. Our first guy was right. You can totally do this in a microsecond. Ruby isn't that slow. Except it's not that simple in our case. If we take a step back for a second, I'm talking about storing these numbers in hashes. But why? Why are we using hashes instead of integers? Well, the reason is you generally don't want one value for your metrics. You may want more resolution than that. For the example of payments, you don't care just how many payments you took, you want to know how many in each currency, right? So we have this concept of labels. Labels are these key value pairs that you can tag your counters with, and we store our counters in a hash whose key is also a hash, which has these key value pairs. And why does this matter for our performance numbers? Well, if you think about how a hash looks, when you try to set a value in a hash, you need to find which bucket inside the hash your key fell in, and then compare your key with all of the keys in that bucket until you find the right one, right? If your keys in the hash are constants, then that comparison is really fast. But when your hash key is also a hash, now in order to find your key, you're comparing hashes to hashes, which is much slower than comparing constants to constants. And how slow basically depends on how big these hashes with the labels are. So, for example, if you have 3 labels for your metric, that's now 60 times slower, which is terrible for us, right? Now, how about a best case scenario? In theory, most metrics shouldn't have any labels, so we can use an empty hash as our key. Let's see how long that takes, and that's better, but it's still 9 times lower than just setting a constant key. And you'll notice we're now getting quite close to our 1 microsecond budget, and we're just incrementing the key here. In real life, we need to do some validation and some processes to these labels, and we're not even thread safe. You put a mutex around it to be thread safe, and now you're in a microsecond and a half, and we blew our budget. So this is how guy number 2 was right in the end, right? We can't do this in a microsecond. But what I think is more interesting is not which one of these two is right. Is that I just wanted an easy answer. I wanted one of these two to win, right? But there's no winning here. Like, reality is more nuanced than that. And this is what I'm talking about when I'm saying that fast and slow are meaningless without a context. It's always more nuanced than that. Bottom line, we can't hit the target of incrementing our context in a microsecond. We're already way past it, and we're still in a single process, right? We can optimize this code a little bit, but doing anything that's going to actually solve our multi-process issue under a microsecond is definitely not going to happen. But we shouldn't throw the baby out with the bathwater here. We can't hit our target, but we can try and follow the spirit of it. The idea is, because instrumentation shouldn't affect your performance, we want this to be as fast as possible. And because this is going to affect lots of projects and lots of companies, it's really worth investing a lot of time to make that as fast as we can, right? So it's not very nice. We now have a baseline. We know how this very basic thing takes. It's not very pretty, but we haven't actually started solving the problem. And so how do we do that? Well, we experiment a lot. We had made it really cheap for us to try everything at this point because we had these abstracted stores. It was really easy to make a new one. So we just tried everything we could think of. And I'd like to walk you through 4 of these experiments that we did. First up, let's make this really easy for ourselves. Ruby has this unusual data structure called APstore. Basically, it's a hash backed by a file on disk. Every time you set a value, the whole thing gets serialized and put in a file on disk. Every time you read a value, the whole file gets read and you get your value back. And the file has a lock around it. So you can actually read and write the same file from multiple processes all at the same time. Everybody sees the latest information and it's safe. And to use that, they use almost exactly like a hash. Now, APstores have this idea of a transaction, which lets you change several values all at once without hitting the disk for each one, which is quite nice. And so you just wrap your accesses in one of those transactions and you're done. And if you think about it, this is exactly what we need, right? We have this global hash shared by everyone. Everybody sees the latest data. We're done. The only extra requirement was that this has to be fast. And as you can probably imagine, they're really not. This is not going to work. So again, let's try and take a step back here. And just, what are we really trying to do here? Well, basically, we're trying to have a chunk of memory that is shared between different processes. And as a complete side note, one of the great things about working in my company are the amazing people I get to work with. Now, granted, some of those people are trolls. But the trolls sometimes have good ideas. I mean, SQLite was probably not going to be the best way to do this. But he got me thinking, you know what's a great way of having a chunk of memory shared between our processes? It's my old friend Redis. Redis is basically a chunk of memory running in a separate process from your app. All of your web server processes can access it, read and write it, and we all know it's super fast, right? So sounds like exactly what we need. And actually, the Prometheus library for PHP uses Redis precisely for this, so that was promising. So I wrote up a little store that uses Redis as a backend, and I was super excited because I knew this was going to be the solution. Fired on my benchmarks, and I mean, that was disappointing, right? Like, it's slower than just dumping the entire hash to disk every time. Now, I was very sad when this happened because I thought I had it, but also, how? I mean, how can it be this slow? Isn't Redis supposed to be super fast? Now, if you think about it, it kind of makes sense. I mean, you talk to Redis over the network, even if it's localhost. Every time you need to touch it, you need to make a packet, put it into a socket, send it over, Redis gets that, opens it, parses the command, runs it, makes a response, packet, socket goes. There's a lot going on. I mean, Redis is really fast for a database. It normally lives in its own server, out in the network. And those 60 microseconds which I saw, they're nothing compared to the network round trip. So Redis is really fast compared to other databases out in the network. But compared to other things that happen in your own machine, in your own process, like writing a tiny file like the APstore does, never really had a chance. So once again, fast and slow without context don't really mean anything. And at this point, I had no choice but to face the giant elephant in the room. The consensus from pretty much everyone on how to solve the multi-process issue was that we should use memory maps for this. This is, for example, what the Python library does. But during most of the project, I was trying really hard to avoid them. I really wanted to find another way. And if I'm being honest, the reason I was trying to avoid them is that I was scared of them. I mean, I didn't know what a memory map was. Before this project, I hadn't even heard of them. I didn't know how to use them. It wasn't really very clear what to do, so I was a bit scared of them. The best thing you have is this, the kernel docs. And they're super useful in the details of how each individual flag works. But if you don't know what this thing even is, this is not a great primer. And I also saw some code examples. This is from the Python library, which left me even more confused. I mean, it looks like the way to get a shared memory, a chunk of shared memory, involves a file path in TMP. Like, that makes no sense. I thought we were trying to not use files, right? And turns out the reason I was so confused is that emmaps are one of the most basic, fundamental building blocks of the kernel. This is not a thing you use to share memory between processes. This is like one of the big tools to use to do all sorts of memory stuff. And the problem with the docs is that they're describing each individual tool in that thing, but what I was looking for was the big picture. But it turns out, for the problem that we have, we care about one of these tools, which is the shared memory mapped file. The way this works is basically a process opens a file and maps it to a page in memory. If you read that memory, you get the contents of the file. If you write to that memory, the file eventually gets updated somewhat later, down the line, whenever the kernel feels like it. But here comes the magic. If another process maps the same file, saying that it wants to share it, both processes get the same page in memory. And so if one of these processes writes to that page, the file will eventually get updated somewhat later, but you don't care about that. What you care about is that the other process can immediately read that page in memory and get the new data, which is magic. And the other thing you also care about is that there's a file, but you're not really writing directly to the file. You're just writing to memory, and it's as fast as writing to memory, not as slow as writing to a file. And it is famously one of the fastest ways to do inter-process communication, right? So I can see why everyone was suggesting to use this. It sounds like the perfect solution. There's only one problem. Emup is a syscall. Do you guys know how to do a syscall in Ruby? You don't. You do it from C. Now granted, there's this thing which has the most hilarious line I've ever seen in official docs. But it's not particularly useful for this. And let's say you actually manage to call Emup with this. Now you have a chunk of raw memory and a pointer to it. Now what? How are you going to read and write that from Ruby, right? Now what we need is some sort of wrapper, some gem, and it has to be written in C. And I don't write C. I can barely read it. I should definitely not be trusted to write some C code that deals with a syscall I just learned about that I don't fully understand. And it does some magic memory voodoo, and it's going to run not only in my company, but in production in a lot of other companies. This is not going to happen, right? But fortunately, there's this gem, which was made by a gentleman called Guy Decoux. But if you look at the repo, you're going to see a lot of this face these days. Now that is a face I trust. This guy, I'm serious, this guy knows C. He's normally doing magic memory voodoo, right? Like, this is definitely good news. In case you don't recognize this, this is Aaron Patterson, who goes by Tenderlove on the internet. He's one of the core Ruby maintainers, and he's currently working on the garbage collector. This guy knows about memory, right? So that's good news. How do we use this gem to Emup? Well, you basically make a file, you initialize it to a certain size, say 1 megabyte, and then you init an Emup. And now you have this M variable, which behaves sort of kind of like a byte array. Now, very importantly, this is not a Ruby array. The Emup gem is doing a bunch of magic to make it behave like one, but it does behave like one, so you can just pretend it is. And if you have a bunch of bytes to write, you set a range on this array, basically, and that'll do it. Now, the tricky bit is turning the stuff you want to store into a bunch of bytes. To do that, you use these methods pack and unpack, which will turn your Ruby stuff into bytes and then back into Ruby stuff again. But if you've never heard of pack and unpack, don't look them up. Keep the innocence. It's really nice to not have to know about this. But in our case, we have a float, and we want to write it into this M thing. So we pack our float into bytes, and that takes 8 bytes, and then we set the positions in the array, and we're done, right? Magic. Couldn't be simpler. Now, how fast is this? Well, as a recap, if you remember, we had a hash with no synchronization at all, which was just under a microsecond. We have a hash with a lock around it, which is for single process multi-threaded apps, and that's about a microsecond and a half. And we have the most reasonable solution we have so far for the multi-process problem, which is about 35 milliseconds, a microsecond, sorry. Memory maps, which as I mentioned, I really don't want to use, are actually quite fast, which is a bummer because I'm going to have to use these, right? And again, it looked like we're done, and I thought that too. But in addition to my tests for this, I have and my benchmark script, I have this other script which stress tests these stores. Basically, it's a script that will do terrible things to them to make sure that we're safe. It will basically run from a ridiculous high number of processes with a really high number of metrics with a lot of labels, everybody just hitting the same files, competing at the same time, just hammering it to make sure it's solid. And as soon as I run that script on the Emup store, now raise your hand if you've ever seen one of these that was your fault. Exactly, right? I got 2 hands, 3 hands. Oh, I find that's more than usual. I mean, the point is you're not supposed to see one of these, right? This is the famous segfault or segmentation fault. Or technically, I think this is the segfault even scarier little sister, which is the sig bus. It's basically the kernel telling you really screwed up. And I don't know about you, but one of my favorite things about working in high-level languages is not having to deal with this. Like, I don't want to have to deal with this. I don't know how to deal with this. I don't know where to start. Right? This is why I don't do C, so I don't have to deal with these things. But I asked around, and apparently this looked like garbage collector related. So like something was freed, and it got cleaned up, and I was still using it, right? But the problem is, what do I do with that? As far as I knew, I wasn't freeing or not freeing anything. I was using this gem that gives you this thing that looks like an array, and now I got a segfault in my face. Like, and this is precisely why I was avoiding these things. Right? Like, I was worried this exact thing would happen, and now it did. And I mean, given that this gem was written by Tenderlove and it was being used by me, it was almost certainly not a bug in the gem. I'm almost certainly doing something wrong. But this is a very obscure gem. There's not that many people that are trying to do Emups in Ruby. I haven't found anything in Stack Overflow. I haven't found anyone actually using it. So it's kind of hard to figure out what I'm doing wrong. But this is what I managed to find out. The problem seemed to be happening when the initial size I gave the file, that 1 megabyte, wasn't enough. I had some code in there that would resize it. And the segfault would only happen if that code had run, but not immediately. It would happen a little later, which kind of points to a garbage collection, right? Cool. So we have no idea why it happens, but at least we can reproduce it reliably. So how do we fix this? The same way we always fix these problems. We just try random stuff until something sticks. Now, it took a while because I had no idea what I was looking for, but I ended up actually making the segfault stop. It was this elaborate dance of unmapping, flushing the file, closing the file, reopening the file, resizing it, closing it again, then reopening and mapping it again, and somehow the segfault stopped happening. Now, if you have a problem, you don't understand the problem. You try random stuff until the problem stops happening, but you don't know why it was happening or why it stopped. How confident are you that that's not going to happen again in production in some random company, in some random mission critical app, right, in production? I really wasn't any confident with this. I didn't like it one bit. And in addition to that, there are other downsides to using the Emup gem, like we were introducing a C extension dependencies. These are the ones that get compiled when you install them. Like, they have a bunch of little problems. It doesn't work in JRuby, for example, and we do want to support JRuby. But I'm sure like a lot of you probably had trouble installing Nokogiri at some point in your life. Like, C extensions can be a pain. But most importantly, it may be kind of segfaulted, so we weren't very happy with this. So it was fast, but we wanted to keep looking. And this leads me to our last experiment, which, of all the interesting things we learned in this project, this is the one that surprised me the most. Now, with the memory map, we were basically working with a thing that looks like a file, doing the kind of things that you normally do with files. We just happen to be doing it in memory instead of with a file, because it's faster than files. But what happens if we ditch the Emups and we just do this to a file? I mean, pretty much the only difference in the code is that instead of setting in a range in a thing that's pretending to be an array, we need to call these functions to seek and write, right? And that's it. And the interesting bit here is that we are only writing the minimum amount possible. We're not, marshalling and dumping the whole hash to disk every time like the APstore did. We're just doing one seek and writing 8 bytes. It's very efficient. And that's pretty much the whole change. And now we have no Emups, we have no C, no segfaults. There's nothing fancy. It's just plain old boring Ruby writing simple bytes to plain old boring files on really slow hard drives. But as usual with these solutions, how slow is this going to be, right? And before I tell you that, I want you to visualize how slow disks are. I mean, We use Redis and memcached famously because they're in RAM and not in disk. We use RAM drives and tempfs, so we can work with things that behave like files, but without actually having to hit the disk because they're slower. We give our databases just gargantuan amounts of RAM so that they can keep everything there and not have to hit the disks because the disks are so slow. So how slow was this solution based on disk? Well, if you remember, the memory maps were about 6 microseconds. Files on actual slow hard drives, what, 9? Which, considering how slow I expected this to be, just completely blew my mind. If you compare this to memory maps, we have no external dependencies, we have no risky C code, definitely no segfaults. It's compatible with all editions of Ruby, like JRuby. It is 100% understandable by any Ruby developer. And most importantly, there's nothing in there that keeps me up at night. All of this, for just 3 extra microseconds, this is a complete no-brainer. And that's it, right? We ended up going with disk as our end solution because it was fast enough, and we think that the trade-off in safety is more than worth it for the change in performance. And this is where my talk should end. I mean, we solved the problem with a fast, elegant solution. We got our code merged. We're now maintainers of the gem, actually, which is quite nice. And now people can use Prometheus in Ruby, right? Happy times. But this, I mean, I don't know about bits, but like this is a funny result, isn't it? I mean, memory is supposed to be many orders of magnitude faster than this, like thousands of times faster. And I'm telling you this, what, 30% faster? Like, what's going on here? And as I've been saying, there's always more nuance than that. Now, first of all, memory should take nanoseconds, not microseconds. And what's going on there is, as I said, it's not really a Ruby array that you're writing to. You have this gem that's doing a bunch of memory voodoo, and it has to synchronize, and it just takes a bit, right? But most importantly, if you're at all used to performance numbers involving disks, you're probably looking at this number with a lot of suspicion right now. And you'll be right, because what's happening here is that I'm basically cheating. Now, it's a fair cheat. It works for my use case, but I'm still cheating. You see, actually putting stuff on a disk is slow. But this is not what happens when your app writes to disk, at least not on a modern operating system, right? When you tell your OS to write to disk, the OS takes note of that and go like, yeah, all right, I'll do that at some point. But it doesn't actually write to disk right there. It will do it later at its leisure, whenever it happens to be convenient. And normally, this is a problem for you, because if you're a database and somebody sends you data, would you trust this dude to actually write it to disk? I mean, of course not, because when somebody trips on the power cable before the OS finished chilling, you've lost your data, which in the database world is generally known as not good, right? So what you have to do is you fsync, which is basically telling the OS, hey, that thing I told you to do it now, I'll wait. And that is slow, because now you're actually hitting the disk. Now, if you're a database, unfortunately, you really, really care about this data that you're writing. So you're going to have to pay that price. But I'm just storing metrics for this particular run of my app. And if my app gets killed, nah. I mean, Prometheus has the numbers so far. Next run of my app, I start fresh from 0. I don't care if that data stays. I only care about it while I'm running so that the different processes can read each other's numbers. But once I'm dead, whatever. I'm starting over anyway. Which means I don't have to wait for the data to actually get committed to disk. And now it's not slow anymore. Because when I'm writing to disk, I'm just writing to that little bit of memory where the OS is keeping track of the things that it's going to write to disk, which is cheating. But it doesn't mean you can't do it. It just means I have a really unusual use case where I can just get away with it. And so, is memory fast? Are disks slow? Well, as I've been saying, it depends on the context. So, I've just covered a lot of weirdly specific ground right now. But what is the point of me being here? Like, what am I trying to say? There's this age-old saying when talking about performance optimization, you've probably heard it. Measure before you optimize. Because the thing that you think is slow is not the thing that is actually going to be slow most of the time. And we all know this. And when I was trying to figure out where my code was spending time, I definitely measured, and I definitely found surprises. I found many cases where the code wasn't spending time where I thought it was. You know, like the experts said, they were right. But what I found in this project is that that's not enough. As I said at the beginning, this is not a talk about memory or disk or microseconds, files, or hashes. This is a talk about assumptions. When we decided that the solution to a performance problem, where we need to do things really fast, was to put stuff on disk, I was shocked. I was completely stunned. And the reason I was shocked is that, like everybody else, I knew that disks are really slow. In fact, if you told me before this project that Marshall dumping a whole hash into a hard drive would be twice as slow as getting a localhost ready server, I would have laughed you out of the room, because I just knew that's clearly not true. But here's the problem with these things we all know. They're normally very simple. They're very memorable. I mean, they have to be, right, if they're going to spread and stay in our heads. Ruby is slow, or Ruby can't possibly be that slow. Surely you can read and write a hash in a microsecond. Now, can you? Yeah. Can we? Well, no. I mean, we're doing something weird with them for good reasons, and it's slow. Memory is fast. Disk is slow. Redis is fast because it doesn't use disk. Now, is Redis fast? Yeah, for the database, it's really fast. Is it faster than disk? Well, it depends. The problem is there's a lot of nuance around these simple truths, and it gets lost in the process. Like, if you look at them up close, these questions aren't simple. They don't have simple, straightforward answers. And everyone that believes these things hasn't actually checked them in the context of their own problem. I mean, of course not. You already know they're true. But the reason that's a problem is that having these things we all know are true is going to make you blind to other potential solutions that you would otherwise see if you didn't have that knowledge. Take this project, for example. It's not like at the beginning we all got together and we discussed the options and we decided disk is probably going to be too slow, so we're not going to do it. It's like, it didn't even cross our minds. We never even considered it, because implicitly we all knew it was going to be too slow. It's like, I actually stumbled on this by pure luck. I happened to notice that the memory maps were open in a file anyway, and we were doing the kind of things that we do with files, and it would be easy to make them do the same thing but without the memory maps, so I tried it. But I didn't try it because I thought it would be an actual potential solution. I just did it out of pure curiosity. I knew it wasn't going to work. I just wanted to see how ridiculously slower it would be. And if I hadn't, to this day I wouldn't sleep well, wondering when that segfault was going to hit someone in a server in production. So what I'm trying to say is, when you're trying to solve a problem and figuring out how to approach it, try to be aware of that filter at the back of your mind that's discarding options because you know they wouldn't work. Just try and pause and look at those options. Like, why do you think they wouldn't work? Are you sure that's actually true? Can you do a little experiment? Can you measure it? Because there may just be a really simple, quick solution that you're missing because it wouldn't work. Sometimes it does. Thank you.